That's wonderful. So here you are, the floor is yours. Thank you.
Perfect. Can you hear me? Excellent. Hi, everybody. I'm Karen Camp. I'm a math teacher and math education consultant from Connecticut and a Geogebra ambassador. And I'm so glad that you are coming here with us today to join my Pythagorean party. Okay, let's begin. First of all, whoops, we are here at the Pythagorean party. Like I said, my name is Karen Camp. You can find me on Twitter at Karen Camp. And if you're going to tweet about this, do the hashtag FLGGB. Here's a little funny from Sandra Boynton about the Pythagorean theorem. You know, you have your opposite, your adjacent, and your hippopotamus. And what I'm going to share with you today is 3 lab activities on the Pythagorean theorem that use the action, consequence, reflection cycle. This cycle helps students get engaged in the learning and to make the math concepts stick. First, students perform a mathematical action and they observe a mathematical consequence. You can ask questions like, what did you observe? What changes? What stays the same? And the final step is to reflect on the result and reason about the underlying mathematical concepts. So I use this action, consequence, reflection cycle on technology activities. The first important point is to use sliders and other dynamic elements to engage students in the action consequence environment. GeoGebra is perfect for this. Students can do things themselves and really become engaged in the math, not just watching the math. I like to say, do the math, don't view the math. The second important point is that although there is certainly a place in geometry classes for students to do constructions on their own, I make great use of a pre-made file so that students can focus on the implications rather than the construction details. The third point is the idea of what happens after students interact with the GeoGebra applet. Students who just look at it, play with it, and then do nothing else, we run the risk of them forgetting what it was that we were teaching or not necessarily learning what we were teaching in the first place. So I try to require students to record their observations. They can do this on a paper lab handout. I have PDFs included with all of these activities I'm going to share with you today. You can also do it on through GeoGebra Classroom or on a Google Doc or any other way that works for you in your classroom. After they record observations, ask for predictions, discuss conclusions, and students can do this with partners or in the whole class. But the key thing is that once the exploration activity is over, we need to summarize the results with the class. Whether I, as a teacher, ask the class to contribute what they noticed, or students can lead that discussion, we need to make a summary, a class summary, to make sure students have learned the objectives we want them to learn. What is the math that they are responsible for? Clarify any misconceptions. You might find some productive avenues for further exploration, but this way you're going to make the math stick, and they're not just going to forget what they're doing. Okay, so let me now bring you to our Pythagorean party. The GeoGebra book that we're going to look at today is bit.ly/pythpartygbb with the P's and the GGB in uppercase letters. So when you go to my Pythagorean party, I'm going to show you 3 lab activities today. We're going to go through 3 of them. And then I have a few more things at the end that was a little help from my friends, because wouldn't be a party without help from my friends. So let's begin with the Pythagorean theorem, the sort of beginning of this. And this activity is based on the geometric meaning, the geometric environmental interpretation of a squared plus b squared equals c squared. So when students get here, they can move the points A, B, and C. They can move them all around and they can show side lengths. But where we're going with this is we're going to show the squares on the sides of the circle. And when you're involved in a dynamic environment and you have students move and observe, it's important that you ask them to observe. So the Geogebra activity says here, what do you notice about the side lengths and the squares when points A, B, or C move? Here is the, can you see this? This is the PDF that also goes with the Geogebra activity. So there's a little warm up in the PDF. Which letter symbolizes the longest side? Move one of the vertices to change its shape. What do you notice? What happens to the side lengths of the squares when you drag? So this is the paper PDF that goes with this interactive Geogebra activity. So what do you notice about the side lengths? And you can record the area data in this chart. So you can record the square area on side BC, the square on side AC, the sum of squares, and the square on side AB. And they can record this in this chart, which is just a GeoGebra spreadsheet. And finally, they can make a conjecture and show the calculations. And they can see that as we move things around, the sum of the two small squares always equals the large square. I've also created some construction notes, so if you want to construct it yourself, they are attached to this. Moving along to our second activity. This is Pythagorean triples. So in this activity, the triangle has been constructed so that the side lengths are always whole numbers. You can grab the open circle vertices and drag to change the side lengths. And with students just playing around, they might find themselves in a situation where they have created a Pythagorean triple, a set of side lengths that has a whole number hypotenuse length. And here, students can they can record their data here. If the sides, even though they're whole numbers, if they don't have, if they have a common factor, a greatest common factor, you can divide by that to come up with a primitive triple. Oh, I'm sorry, I see in the questions that there was a question about what was the, where were we supposed to be? Let's get that in here. Okay, it's bit.ly Pyth Party GGB. Okay. Let's go back to our Pythagorean triples. Okay, so here students would have found 6. Oops, that's not supposed to be there. 8, 10. And the greatest common factor of the sides is 2. And so if you divide each side by the 2, you get 3, 4, 5. Whoops, that is not going to work. 3, 4, 5. I have to change that so that you can type that in with commas. Okay, so whoops. That gives students a big canvas here to work on and let them try and find some of these. 8, 15, 17 is another one. And so students, you would go through with your students that not only can you find a primitive triple by dividing by a common factor, you can also scale up to create new triples. So in the lab handout, again, students are working from the same information. They're going to record their data. If there's a greatest common factor of the three sides, enter that in your fourth column and divide. There's a little check for understanding, determine if these are Pythagorean triples. And the fifth step here on the lab handout is create a Pythagorean triple with a primitive triple you found above, multiplied by a scale factor. So here we've got 8, 15, 17. We could double it and make it 16, 30. I don't know if I have room for 30. Maybe I better make the 16 here. 16, 30, 34. And so then I can confirm that my triple is correct. And the last part of this lab activity was really fun. There is a formula to generate a Pythagorean triple. It's Euler's formula. If you use two numbers, m and m, as long as m is larger than n, you can create a triple. And the triple, you can enter these numbers into an input box here. And so I began with m equals 2 and n equals 1, and that generated 3, 4, 5. If I change my m to 3, we now get 8, 6, 10. So this generator won't always generate a primitive triple. If I do 3 and 2, now we have 5, 12, 13. And you can see what happens if we mix up our order and we put n as a larger number, we get some negative value. If we use the same numbers, we get a 0 value. So it only works, it only gives us a value, a set that's a triple, if m is bigger than n. So there's lots of opportunity for students to play around with this. So use the generator below to create a triple and then test it with the triangle above. And so that is the second activity. Also on the PDF lab handout, the same information is there. There's also an extension in my PDF. I don't know about you, but I've found whenever I have students working with technology, there's always students who are working more quickly than others. So I try when I can to include an extension for fast finishers or students who want to explore more. So this extension is written in a very general way, but there are some very interesting patterns in the numbers that make up Pythagorean triples. What do you notice? And I didn't say anything else, but they can look at odds and evens. They can look at factors of the triples. And so there's some really interesting number theory around that. Before I move on to my third activity, are there any questions that we haven't dealt with? You can ask them in the Q&A. I can also tell you that when I use technology with students, there's different ways that you can set up the technology environment and how to generate discussion with your students. So something I always used to do is back in the day, I would have students going to a computer lab because we didn't have handhelds or individual laptops in the classroom. So I got used to having two students working on the same computer. The reason why I'm mentioning that is because students now often are working on their own individual devices. And if you want to encourage discussion between students, consider having your two students working on one device. One student can run the pointer or the mouse. Another student can do some recording on the lab sheet. But that is one way to encourage that discussion between students and encourage conversation rather than having two students on separate devices. Okay, let's move along. Our third lab activity is the converse of the Pythagorean theorem. And this is another one of my favorite activities, an action, consequence, reflection activity. And the GeoGebra lab says, grab and move one of the large blue points to change the triangle. Now, this triangle can rearrange so that what I've labeled in red as the C might not end up being the largest side. but the blue points move. And there's a note to students, be sure the largest side is the one with the red measurement. When I've had students talk about the converse of the Pythagorean theorem, I talk about it as it's really two things. One thing is the converse of the statement that if a triangle is a right triangle, then a squared plus b squared equals c squared. So we turn that around and we say, if a squared plus b squared equals c squared, then the triangle is a right triangle. Here we go. There's an example of that. But I also have students turn around the a squared plus b squared equals c squared. And the reason why I have them turn it around is if we start with the c squared, if the c squared is equal to a squared plus b squared, then it's going to be a right triangle. If the c squared is bigger than a squared plus b squared, then it's going to be obtuse. And if the c squared is smaller, then it's going to be acute. So I always put the c squared first in the Converse Pythagorean Theorem lab. So students in the lab activity, again, are being asked to move things. What do you notice to begin with? Fill in the lengths of the sides, calculate these, and collect data to create several kinds of triangles. Again, a chart to record the data. Do any of your triangles meet the requirements of the Pythagorean theorem? And then what do you notice when c squared is less than a squared plus b squared and c squared is greater than a squared plus b squared? In the lab activity, same questions, and apply the math, predict which type of triangle each one will be, create a set of sides that will make each one. And then 14, what happens if you try to make a triangle with sides 4, 7, 11 or 4, 7, 12? And this gets at the additional issue of the triangle inequality property. Students get so excited about being able to make an obtuse triangle that they try to make, they just pick numbers like, here we go, I've got 6 and 6. So they're going to go 6 and 6 and 15. Well, we can't make 6 and 6 and 15. It will not work. Okay, so students can play around with that. Good. So again, the lab activity is attached, and the construction notes are attached. And what I can tell you is that if you decide to use these in your classroom, and I hope that you will, please consider adapting it and editing it for your own use. If the PDF lab activity doesn't meet your needs, let me know, contact me, and I will happily send you a Word document so you can update it and edit it. But what questions I thought of to ask might not be your questions. But when you're asking questions, make sure you're giving students an opportunity to reflect on what they saw, engage in a dynamic motion, some action, and then observe the consequences and reflect on the mathematical meaning. Okay, what we're going to look at now for the ending of our Pythagorean party, I wanted to make sure that when I teach this to students, the Pythagorean theorem isn't just a fun, theorem that is really important and you should remember it. The Pythagorean theorem is also connected to several other ideas in math class. So on the Geogebra book, I have a little help from my friends, and I gathered a few activities that you may want to use as well. First of all, the Pythagorean theorem is the same thing as the distance formula. And Audrey McLaren happened to publish this activity just a couple days ago. And what she was doing was she was practicing with the distance formula, having students, take a set of numbers and figure out what the distance was. And she has some checkboxes where you can show the X dimensions, show the Y dimensions. The students can figure out the distance. They can check their answer. So this is 3 and 5. Let me move this. There's 3 and 4, and all of a sudden we have 5. And she says right here, the distance formula is just really Pythagoras. Another friend, Tim Brzezinski, you all know Tim, he's done some fabulous things. I said, Tim, I want to show this with a circle. And the circle equation is also the distance formula. So we can change the radius of our circle. That is a 3.16 radius. This is a radius of 3. We can move this point around and show that the radius remains 3. And then moving the slider point, Tim has built in a beautiful Pythagorean theorem right triangle. And so you can see that the equation of that circle comes from taking the Pythagorean theorem using the distances of the sides. Finally, many teachers who are doing the Pythagorean theorem, sometimes you do some of the proofs, the famous proofs of the Pythagorean theorem, sometimes you don't. But Steve Phelps has a fabulous collection of proofs without words, and I have selected some. Let's take a very quick look. This one, we have the two small squares. What Steve has done here is they shear, and that's a whole nother geometry question, which I love, is why is the area the same when those squares shear into those parallelograms? And then they translate down and shear again, and they are the same. A squared plus B squared equals C squared. Here's another one, A squared plus B squared. We dissect, rearrange, and we get C squared. And this side here is A, this side here is B, this side here is C. Here's another one. And finally, we can do one where we are rearranging different pieces of the B squared and add in the A squared, and we get C squared. So I only had a very short time frame to work with. Once again, here is the link to the Pythagorean Party GeoGebra book, bit.ly/PYTH/PARTY-GGB. I've got one more little cartoon for our day from XKCD. This one was called Benders, Bendy, huge geometry breakthrough. Turns out those lines we make triangles out are bendy. So yes, he's created a 5-5-5 right triangle. And you can find me at karen.camp@gmail.com. My blog is karendcamp.wordpress.com, and I will be writing up some of these activities on a future blog post. On Twitter, I'm at Karen Camp, and I'm also in the Teachers Using GeoGebra Facebook page. The materials that were on the individual pages, all those PDFs, let me just get to it, are on the GeoGebra conference page down here. Let me see if I can make this bigger. Okay, so the GeoGebra book is bit.ly/PythPartyGGB, but the Dropbox with the lab activities and construction notes is at bit.ly/Pythagorean Party. So I still have a couple minutes. I'll stop sharing my screen.
Yes, you have, Karen, wonderful. Thank you so much. This is so much fun. And you have still a couple of minutes. We have 10 minutes between the speeches, but I think that let's check the question. Do you see the question?
Okay, are there any questions?
Remarks? No. Great presentation, potentials and things like that. Okay, so you can have a couple more minutes, then if there's no questions, please continue.
Let me put the those notes into the chat. Can the
Wonderful.
Can the participants see that in the chat, or do I have to put it in the Q&A?
see what, no, I think you are just, I will copy that and I will send it to everyone. I am not sure
Okay.
if you have that. Now
Thank
it's
you.
in the chat to everyone from me, but really from Karen. So you have Geogebra book here and Dropbox.
And I have plenty of other action, consequence, reflection, GeoGebra activities, and I'm not the only one who does them, of course, but please feel free to take a look at my other activities at the, here you go, Kasia, if you can share that as well, that's where the rest of my activities are.
Yes, sure. Absolutely.
And my blog.
Wonderful. And
There it is. And once again, so glad that everybody was able to join me for my Pythagorean party. And thank you so much for my friends for helping me out.
Absolutely. Thank you for supporting our conference. It is still, wait. It is coming. Same and different. Okay, this is reflection.
Yeah, that was a recent post. That's a nice post.
Yes, thank you so much. We really enjoy to have such a variety of speakers. We are so lucky. So many people is supporting teachers and want to share the knowledge and time. Thank you so much.
Okay, thank you very much.
Thank you. Thank you. I stop.